MFI Zeolite has wide applications in the petroleum and petrochemical industries. MFI stands for Mobile 5. Mobile was the corporation that first synthesized MFI Zeolite. MFI Zeolite consists of a set of intersecting channels, straight channels in the y direction, and zigzag channels, and the channel dimensions are approximately 5.5 angstrom. The molecules can hop from one adsorption site to another along the straight channels, or hop along the zigzag channels. In the y direction, we can see that there is a straight diffusion path for the molecules to move, whereas in the x and z direction, z being the depth of this diagram, the motion of the molecules has to be at an angle along the zigzag channels, and there is no direct path to the z or y, x directions. Indeed, the objective of this presentation is to underscore the diffusion anisotropy in MFI Zeolite. For background, I refer you to my paper in 2019 in ACS Omega. Watch also the YouTube video visualizing molecular motion in MFI Zeolite. Let us get a feel for the diffusion anisotropy in MFI Zeolite. These four graphs present MD simulations of the self-diffusivities in the x, y, and z directions. The diffusivities in the x directions are indicated by the red circles. The diffusivities in the y direction are indicated by the green squares, and the diffusivities in the z direction are indicated by the blue triangles. These are the self-diffusivities for methane as a function of the loading of methane in units of molecules per unit cell. This is the diffusivity of propane as a function of the loading in molecules per unit cell. We see again that y direction, the diffusivity is significantly higher than that in the x direction, and in the x direction the self-diffusivity is significantly higher than in the z direction. The same holds for normal butane, y direction, x direction, z direction. This is the diffusivity of normal hexane. We see that the diffusivity in the x and z directions are significantly lower than the diffusivity in the y direction. Indeed, you might even argue that the motion along the x and z directions is practically at a standstill for normal hexane. Let's try and understand why this is the case. Another point to note is that the diffusivity reduces to practically zero at a loading of 8. We ask ourselves, why is that so? In this case, the diffusivity reduces to 0 at a loading of 12 molecules per unit cell. For normal butane, the diffusivity is practically 0 at a loading of 10 molecules per unit cell. Whereas for methane, the smallest of these alkane molecules, the diffusivity has a finite value at a loading of 16, and indeed the diffusivity reduces to near 0 at a loading of about 24 to 26 molecules per unit cell. Let's first examine normal hexane, and to see why the diffusivity reduces to 0 at H, and also why is the diffusivity in the Y direction so much higher than the diffusivity in the X and Z direction. Here I show the adsorption isotherms for normal hexane and its isomer 2-methylpentane. The saturation loading for normal hexane is 8 molecules per unit cell, and that explains why the diffusivity reaches a near 0 value at a loading of 8 molecules per unit cell, because the channels are fully occupied and the mobility of the NC6 molecules is reduced to practically 0. Another point to note is that normal hexane has a molecular length that is commensurate with the distance between two intersection sites. For example, this is the view from the top. This is the XZ view to show you the zigzag channels, and the distance between the two intersection sites is practically the same as the length of one normal hexane molecule. Put another way, the location or the adsorption of NC6 is commensurate with the distance between intersection sites. And if a molecule adsorbs in a commensurate manner, it sits cosily within the channels. And for that reason, the mobility of the molecule in the X and Z direction is practically 0 because of commensurate adsorption. The motion of NC6 is predominantly in the Y direction along the straight channels. MFI zeolite is used as a catalyst for xylene isomerization. Orthoxylene and metaxylene, due to the molecular configurations, prefer to locate at the intersection sites. They are more highly constrained within the channels. Paraxylene, being a linear molecule, diffuses much more easily by about a factor of 100 or 1,000 faster than orthoxylene and metaxylene because of configurational considerations. And the diffusion of paraxylene is predominantly in the Y direction. And for that reason, xylene isomerization with MFI catalyst produces paraxylene almost exclusively, because the product leaving the MFI crystal is paraxylene that has the higher diffusivity. So diffusion anisotropy is useful in dictating the selectivity of the products of xylene isomerization using MFI catalyst.